Hey, good morning, everyone. Thank you for coming back and anybody that's joining us here for the first time. My name is Alex Bassini. I'm the Business Development Manager here at AWC Water Solutions. Today, we're joined by Gregg Semler from In-Pipe Energy. You're down in Portland, Oregon. Is that right, Gregg?
That's right, Alex.
Okay, nice. At least we're in the same time zone. Sometimes we have guests that are 3, 4, or sometimes 8 or 9 time zones ahead of us, and we're trying to line up the hours. So this is great. So for everybody that's been here before, here on the AWC webinar, we touch on normally water contaminants and of course technologies for treatment on the treatment side. This week, we're doing something very different. We're going to go into PRV, or in this case, it's an In-PRV or pressure recovery valves. You'll notice I highlighted or I underlined the recovery front just because it's an important part of understanding how these work. So with that, let's get started. So of course, this is a part series. It started as a 3-part series and it grew into a dozen, and now we're at number 28, and we're going to continue going on this. If anybody has suggestions, please let us know. We've got the next 6 weeks that are booked, but other than that, we're doing pretty good with a lot of new content coming up. So just a background on AWC, of course, you know who we are, but we've been around for 40 years. We have close to 600 plants, both water and wastewater treatment plants worldwide. We divide everything into potable water, wastewater, and skid-mounted systems. And this is what I love about PRV. You could potentially be adding to something, to any one of these, whether you're going to potable or wastewater, and we'll get into it a little bit more. Of course, before we get started, we do have to highlight today is Earth Day. So, we had World Water Day last month. Now we have Earth Day. So my question is always, how are you going to celebrate Earth Day today or this week? And every day is Earth Day. We live here, right? So we don't have a choice. So with that, we're going to bring it over to In-PRV. So Gregg, go ahead, take it away.
All right, thanks, Alex. Let me just happy Earth Day, everybody. I'm Gregg Semler, President, CEO, and founder of In-Pipe Energy. I appreciate you taking the time today to hear more about the NPRV, a pressure recovery valve. So In-Pipe Energy is a renewable energy and smart water technology company that's developed a new product called the In-PRV. It's a pressure recovery valve. And what it allows is water departments, water operators, to precisely manage pressure, just like what they're doing today, but to take that available pressure, that excess pressure, and convert it into a new source of renewable energy. With the In-PRV in place, a water department can manage pressure precisely, but reduce their operating costs, save carbon, save water, and extend the life of their infrastructure without changing their current operation. And I'm going to tell you about that now. So as you know, water is the most important resource on the planet, but it's also very energy intensive. So for many of our customers, energy is their second highest expense, and oftentimes can be over 40% of their budget. Water is conveyed similarly all over the world. Water is pumped up a hill at night, stored in a reservoir or overhead tank, and then distributed through pressurized pipelines into the service area. And these pipes are pressurized either by pumping or by gravity. And what water departments do is they manage to deliver safe, clean drinking water at a specific pressure, so that when one of their ratepayers turns on the shower in the morning, for example, it comes out at the right pressure. Well, the way they do that is using control valves, in particular pressure reducing valves or PRVs. And these PRVs are distributed throughout a water distribution system. We worked with Mueller Water, one of the leaders in valve technologies in the United States, and sized our market as an opportunity to recover about 12 gigawatts of potential energy if we were fully deployed throughout the United States and offset about 38 million tons of carbon annually. This would be a savings to the water industry of over $60 billion and would be significantly free up capital that could be used to reinvest in water infrastructure and make it more resilient. So this is a typical pressure reducing valve. I'm sure most people on the phone have seen these. This is the inside of a pressure reducing valve. And pressure reducing valves do a great job of managing pressure. But the way they work, they basically use a mechanical mechanism, a spring with a diaphragm that is set to take out pressure. So water departments, if they, let's say it's 100 feet on the upstream and they need it to be 60 feet, they set the diaphragm to take out 40 feet of pressure. And they kind of work like the brakes in your car. They're set, and then the pressure is dissipated through friction or heat, and that allows this process to occur to get to the right pressure. But the way they do that wastes this excess pressure that could be used as a new source of renewable energy. And that's kind of like how the Prius works. If you're familiar with that mechanism in the brakes, they call it regenerative braking. And that's basically what In-Pipe has done with the NPRV. So this is a picture of the NPRV in a existing vault facility. There's a main pipeline and a PRV, and we're co-located at these particular sites. The NPRV is basically combines micro hydro technology with control technology and a control system that allows the NPRV to work compatibly with your existing facility. The NPRV is designed to be turnkey, really easy for you to install, operate, and maintain the system. And once it's in place, it works automatically to manage pressure and then offset your energy costs to turn those into energy. It also sends out data. It can be integrated into a SCADA system, or it provides real-time 24/7 hydraulic data, flow and pressure, energy generation, and carbon reduction data to an iPad or an iPhone, a device like that remotely. And because we are taking advantage of hydroelectricity, this is the lowest cost source of renewable energy that you can have. So the way it works is we basically work with water departments. We understand where their valve locations are, and then we work to try to understand the hydraulics. We do a free hydraulic analysis and economic assessment. And once we get through the process of knowing that this would be a great place to do energy recovery, we basically build a bypass around the existing valve. And we use hot tapping if we can, so that we can put a hole in the pipe without turning the water off. And then we put in these two gate valves. We install the NPRV and a control system. And basically then what happens is that the water department basically says, it's time to take out pressure. There is a flow control valve inside the NPRV that opens up, and water naturally flows into the bypass, where there's a micro turbine that spins a generator that's connected to the grid, electric grid panel at the facility. It meets all the requirements that have been established by the solar industry, so the electric utilities find it safe and compatible with their regulations. The water flows through the microturbine to a downstream pressure reducing valve that's set at exactly the downstream pressure that the water department needs it to be. And then the water flows back into the main pipeline at the exact pressure that the water department requires and into the service area. So this is all done continuously and naturally without any intervention by the water department. But it allows the water department basically to choose whether to manage the pressure using their existing setup, which is still there just the way it was before the NPRV was installed, or to use the NPRV to manage pressure and generate a new source of renewable energy. So as you know, there can also be variability in the flows of water in these pipelines. It can be daily variability, it can be seasonal variability. The NPRV is modular so that we can install multiple NPRVs in place at a facility, and then our control system will automatically determine which is the best NPRV for a given flow and pressure situation that it may occur, either, as I said, either on a daily or monthly or seasonal requirement. The ideal conditions for the NPRV are where you have existing control valves that are taking out pressure. So we need pressure differential. We need either a PRV or a sleeve valve or a control valve to create the setup so that the water will flow into the bypass. And then we take out that excess or wasted pressure. It's usually behind the meter or where we can offset important or energy intensive equipment like pumping facilities or purification facilities, things like that. Or we can connect it directly to a grid or to an EV charging station, a hydrogen electrolyzers, anywhere that you need low cost energy the NPRV is a great source for that opportunity. Usually we go into gravity fed systems. That's usually where the PRVs are. But we could also go into outflows, effluent streams, post-treatment water streams that are flowing to fill aquifers, fill wells, going back into a river. Wherever there's excess pressure, we could use the NPRV to recapture that energy and help water departments reduce operating costs due to electricity. Typically, our system will go into pipe diameters in the 8 to 42 inch range, but it really comes down to hydraulics. So we need a minimum flow of around 3 CFS up to maybe 50 CFS. The most important metric is pressure. We need to be able to take out about 80 feet of head pressure in order to make the economics really viable for this technology. So the amount of energy that you can produce, it's a simple physics equation. It's just available pressure, the flow rate, and the system efficiency. Our system efficiency is about 80%. So depending on the amount of pressure is available to take out, times the flow rate will determine how much electricity you can produce. And you can see from this table that if you start to get significant amount of head and flow, you can start to generate a significant amount of electricity as well that can be used to bring money back to the water department. So In-Pipe is currently at the stage where we're doing field trials in the United States and Canada with water utilities to help us improve our site selection protocols, our design standards, and our business models. And typically In-Pipe will fund the design, the installation, operation, and maintenance for an installation without any out-of-pocket cost to the water department in exchange for an agreement to purchase the electricity directly from us. This is a typical structure that other renewable energy technologies like solar and wind have deployed, and we want to bring the same opportunity to water departments. So this is a recent installation that we did with the city of Hillsboro, which is a suburb of Portland, Oregon. It's a very industrial area of Oregon. And what we did was we went to the water department in the city and identified this pipeline on the far left. This is an 18-inch water pipeline feeding Intel's largest fab, the city of Hillsboro's most important customer. And you can see the PRV and a low flow bypass here and another PRV. And then so we did a hydraulic assessment, and you can see over a 12-month period in the blue bars sort of the variability of the flow. So we designed the NPRV to be consistent in terms of its energy production, installed the system, which you can see in this picture, at a sports complex at the city. So now when the water flows through to Intel, Basically, we're producing about 200,000 kilowatt hours of electricity a year. It's enough electricity for about 25 or 30 homes around the clock from free electricity at the city of Hillsboro, offsetting about 6.3 million pounds over their project life, which is an important goal for their sustainability plan in the city. Some of this was funded by the city of Hillsboro and the local utility, as well as some electric utility programs that were available. This project has been up and running. It's operating beautifully. The operators are using it at peak flow, and we're talking to them about doing a second and third project. So again, typically what we do is we meet with water departments. We do this hydraulic assessment. So we look for data. We want to understand your flow and pressure at your PRVs. And then what we do is we do an assessment. We come back to you with basically a report that shows, what this would mean to you in terms of energy recovery and economics over the lifetime of the project, which should be 30 or 40 years. And we do all of that for free. We have a very specific process that we use. We call it 10 steps to a successful project. So we meet with you, we do this hydraulic analysis and potential energy assessment. We do a site visit. We do a further economic assessment. We work toward a sort of a non-binding memo of understanding, just so that we can agree on what we are going to try to accomplish together. Then we do a detailed design proposal, a system layout, a schedule, and a budget. We bring in mechanical and electrical contractors to install the system, do a contract. We do the regulatory permitting, the interconnection, the PPA application to the electric utility, and the installation. And we do all of that for free. We're happy. We love to do all these applications and paperwork so that the water department doesn't have to. We do it all collaboratively, and there's no charge for any of it, except for ultimately either a power purchase agreement, or oftentimes the water department really just wants to purchase it themselves so that they can take advantage of all the economics. So love to spend time exploring ways to collaborate with you, and I appreciate your time. I look forward to further conversations. If you want to contact me, I'm Gregg at impipeenergy.com, or you can call me at 503-341-0004.
Excellent. Thank you, Gregg. I'm opening it up now to some questions. I have a short list of questions on my own, but everybody, please don't be shy. You can either turn on your mic or your camera, type it into your chat box. We are already getting a couple questions coming in. So here's the first one. You know what? That was on my list. Thank you, Sheldon. So question number one, what is the maximum water supply pressure and minimum differential?
Yeah, so the maximum water, we've looked at water pipelines that have 30-40 million gallons a day of water that we can address with the NPRV in the current product. And then the minimum differential pressure is really around 80 feet. Like if you get into those really high flow ranges, let's say over 10 million gallons a day, then we could probably do a little bit less than 80 feet. But I think 80 feet really kind of fits really well in terms of what the micro turbine wants to generate in terms of a meaningful amount of electricity.
Okay, thank you.
Question.
Thank you, Sheldon. So, I loved how you use the micro hydro. Here in Canada, a lot of our power is generated through hydroelectricity. So I think the micro hydro concept kind of narrows it down to kind of, oh, okay, I get it. And we are, displacing energy more than anything for generation. Now, being the water nerd that I am, I guess my first question is going to be water quality.
Yeah.
So what are the water quality considerations for something like this?
Yeah, so typically we're going into drinking water systems or post treatment water. We can be in water reuse, for example. You don't want particles going through the turbine. It really just messes up the impeller that spins around. The valve piece of it is pretty okay with different qualities of water, but ideally it would be particle-free water. You could go into turbid water, for example. So we would check that out, and then basically we would coat the parts that touch the water so that, minimizing corrosion and that sort of thing for long lasting.
Okay, thank you. Next question here from Eric is, where has the in-pipe been approved by utilities in North America?
Yeah, so we did this project in Hillsboro. We're in 2 weeks we'll show a project just up and running in just north of Seattle. We're working on a project in the Oakland Bay area. And we have several other water departments in Wyoming, Colorado, Texas, Utah, and Arizona that we're working on projects with as well.
Okay, and since we're kind of exploring, I think the world is really looking at desalination. While I don't think it's always a solution, but certainly there's been a lot of talk about the desalination industry. Can this be used with, like you mentioned, high turbidity water, but something going into the tens of thousands of TDS, whether it's sodium or fluoride?
I think in energy intensive technologies that we're trying to use in the water industry and the electricity industry as well in cities, like for transportation, this is a great way to recover energy and produce a low cost source of electricity. So it would be really good in that kind of a system.
Excellent. Okay,
Yeah.
I had one last question about the multiple PRVs, and I don't think there's any more questions coming in, but you had a picture where you showed 3 of them in series. Is there a maximum that you would recommend if you're running them in series like this? Would you go more than 3, or is 3 to 4?
We've looked at going up to 5. So that's where there's either a lot of variability or they're planning for the future. So we see a lot of water departments, especially in the United States, anticipating a lot of money from stimulus and like trying to figure out how to grow over the next 30 years or 40 years. And as we know, their money's been really tight in the water industry. So this is a chance to modernize for the future. And so we're talking to several water districts about building the capacity to have multiple NPRVs as flows increase over the next 30 or 40 years.
Okay, and I did have one last question, and since we're looking at some industrial applications and projects, is there a temperature range? Would you not use it within a certain temperature when you're going into really hot water?
No, I don't think temperature. It's not sensitive to temperature. I think we can operate in most temperature ranges in all situations that we've looked at. Temperature has not been an issue.
Okay, so now we do have one last question before we wrap up. So we have one here from Tom. What is the typical energy price utilities will buy? I guess that changes from state to state, but.
It really does. It really is completely a function of the electric. I think he's talking about electric utilities. It's really a matter of what's the program that the electric utility has. And in California, for example, it's time of use, and it can vary significantly the price. And in other places, they don't do time of use, but they have specific programs for micro hydro and for small distributed renewable energy. So that's a tough question to answer.
Okay.
What's the range? It can range anywhere from 4 cents to 22 cents.
Right. Yeah, there is going to be a big range, especially when you're going into somewhere like California. Right. Yeah. Okay. So with that, I'm going to wrap up. There's a couple people that are joining us a little late here, but we are going to have the recording. Speaking of the recording, we do have everything on the YouTube channel. Any of our past webinars will be there, and then this will be sent out tomorrow afternoon with a link. So if anybody wants to have a look at that or any of the past ones, we do have one that we will be doing in another 2 weeks. We're going to be touching hollow fiber nanofiltration. We've done membranes before. We've done ceramic membranes. This is going to be very specific to hollow fiber ones. We're going to be joined by an outfit out of Holland as we explore this. So with that, thank you very much. If anybody wants to stick around, and ask Gregg any more questions, go ahead. I did share his contact information there. Well, if somebody can mute their mics there, it's a little loud. But with that, we will go ahead and wrap it up. Thank you very much for being on, Gregg. This has been great. I always love exploring new technologies, especially when we're going where we can tie in the energy and the water nexus. There's always something that we can connect between the two. So
I love it too. Thank you.
Okay. All right. Thank you, Gregg.
Okay.
Bye. Bye,
All right.
everyone. See you in
Bye.
2 weeks.